Hello, everyone, and welcome to your Math 267 Exam 2 Calculus 3 review. My name is Vedang. I'm an executive tutor and I spearhead math operations at the Engineering Tutoring Center. Recently, we've rebranded as Pulse. Today, we have Shobita joining us, and I'll let her introduce herself as well. But before we get to the review, you can find the review at the link that's shown here. It's math.asu.edu/math267, and you can click on the practice 2 test, right? Um, we'll just go over a few basics. Um, how to set up a Math 267 problem because over the few years since I've taken calc and since I've taught calc, these are the four things that have stood out to me. And let's get started. So the first thing being is that read the problem slowly and circle the givens and what you're asked to find. And so many students and individuals have the habit of underlining, the values, circling the givens, or sometimes I myself rewrite the givens so that I know I'm not missing out on anything. Number two is that define your variables and write the function or equation that models the situation. For example, including the domain and any units if they're important. Number three, your calculator must be a friend, and I cannot emphasize on this even more. Your calculator must be a friend and not your enemy, is because I've seen so many students mess up calculations despite their working methods being correct. They've plugged in numbers wrong, and then that's ended up messing with their final answer, right? Set it up in a way that's intuitive for you. Every time you do math or practice math or you're in class, use the same calculator. Familiarize yourself with it. And number four is that interpret your answer in context. Check the units, try reasoning with it. For example, if you're calculating the lift or drag of an aircraft, we know that drag really can be negative, right? It doesn't make sense. So, state your conclusions, make your assumptions, and obviously check if the value is reasonable and, within bounds. Um, you can find us at ECG 152. Um, it's the Engineering Tutoring Center, so we can't wait to see in person as well. So I will now give it off to Shobita, who will conduct the review. Thank you. Have a good day.
Thank you, Vedang, for covering what FSC Tutoring Center is and where to find this review for Calc 3. Hi, everybody. I am Shobita, and I am a math tutor, and I tutor all the calc courses and differential equations, and I'm situated in ECG 152. Today, I'll be going over this Calc 3 review for the upcoming test 2. And this review is mostly to understand how much time to dedicate for every single problem based on how many points it's worth and how much work do you have to show. Um, I always like to start off by reading all the instructions on the exam, no matter how many times I've read them, because um, it's important to understand what problems do you need to necessarily show work for and how to get partial credit by showing that work. So yeah, so our first part is the multiple choice, and for these questions you don't have to show work, but and you're not provided with extra space for this work, and we need to limit our work into this space. You can always go ahead and ask for scratch paper, but the very fact that these questions are multiple choice is because their solution is sort of only maybe a couple lines long. Okay, so for the first problem, we're asked to find the partial derivative of z with respect to s, and we can see that z is a function in x and y. So we'll first of all find the derivative with respect to x, or the partial derivative, and that's just going to be 1, because the derivative of t with respect to x is just going to be 0. Then we take the derivative with respect to s for y. So this would become cosine of s times t and times the derivative of the inner function, and that's just going to be t for our case. I hope it's clear that when we take partial derivatives, we treat everything but the variable that we're taking the derivative with respect to as a constant. So in our case, since we're taking the derivative with respect to s, t would be treated as a constant. Okay, moving on, then we take the derivative of z with respect to s. And this would be, we'll be using product rule here since z is the product of two functions, x and cosine y. So the derivative of x, that's just going to be dx over ds, and times the second function, that's cosine y, and then plus the derivative of the second function, that's going to be negative sine y dy over ds, and then that times x. Now we just plug everything in. So dx over ds is just 1, so this would just remain cosine of y. We can pull the x up in front and the negative sign. So x times sine y, and then dy over ds is cosine of st times t. So cosine st times t. Now we see what option matches our answer right here, and that's going to be the first option, cosine y minus x times sine y times cosine s of t times t. So that's our answer right here. For the next question, we need to find the maximum rate of change in this function at this given point. And to find the maximum rate of change, first of all, we find the gradient. And the gradient of f is just the partial derivative with respect to x and y, right? So we find the partial derivative with respect to x first, and that's going to be 3 over 4 x squared times y squared, and then we find it for y, that's going to be 2 over 4 x cubed times y, which is just 1/2 x cubed times y. Okay, that makes our gradient as this, comma this. Now we need to find the gradient at this given point. So our gradient at 1, 2 is going to be 3 over 4 times 1 squared times 2 squared. So 3 over 4 times 2 squared, that's 4, comma 1 over 2 times 1 cubed times 2. So 1 over 2 times 2. And that's just 3, 1. Now we need to find the unit vector for our gradient. And that's going to be three over 3 squared plus 1 squared, and that's going to be square root of 10. Okay, so the direction that gives the maximum rate of change would be this, and any multiple of this would be the maximum rate of change. And since we have this right here, because the other options aren't multiples of this. Okay, that is the reason we'll just choose C here. Okay, now for the next problem, we have to reverse the order of integration. Now for this problem, I would suggest that you always draw the region that you're supposed to find the integral in. So how do you find that region? You just take the bounds. Okay, so for y, our bounds go from 0 to 2x. So y equals to 0 to y equals to 2x. So that's going to be y equals to 0 starts at the origin, right? And then it goes to 2x. So that's going to be this line right here. Okay, and for x, it goes from 0 to 1. So it goes from 0 to 1. Okay, what would this point be on the y-axis? So this is the region that we're covering. And this point on the y-axis will just be 2, right? And now we have to flip the order of integration. So we have to take the x bounds first and then the y bounds. Okay, so x goes from this, ranges from this to 1. And this is just the line y equals to 2x. But if y equals to 2x, then that means that x equals to y over 2. And x goes from y over 2 to 1, right? Because it starts from this line and it goes up till 1. So it's going to be y over 2 to 1. And for y, it ranges from 0 to 2. So 0 to 2. 0 to 2, your function dx dy. Do we have an option like that? Yes. So B would be the correct answer for this one. Moving on. For our next problem, we have to find the domain. And to find the domain, you always have to think about the function that limits the domain of our function. Or in our case, that's going to be log. And we know that the log of anything, log of a, has got to be always positive, because negative logs are not defined, right? So this right here always has to be greater than 0. Okay. Oh, sorry. Yeah. So this cannot be negative because the log of a negative term is not defined. This is always greater than 0. Okay. Now we subtract 4 on both sides of our inequality, which gives us this. And then we flip signs, which is also going to flip our inequality. Okay, so this should be the domain. And it's option A right here. So yeah, this should be the domain. Okay, now this question is based on contour lines or the contour plot, and we have to find which of the following has the greatest value. Okay, so we have to remember that the greatest rate of increase is in the direction of the gradient, right? because gradient gives you the rate of increase, and the direction of the gradient shows you which direction is the greatest rate of increase in. Okay, and our direction of gradient is perpendicular to contour lines. Okay, now take a moment to think about. Okay, so we draw tangents to our contour lines here, and we draw perpendicular to them. So the greatest rate of increase would obviously be in this direction, pointing this way, which is north, south, east, west. So this is northeast. Okay, and yeah, so it should be C, because our perpendicular points this way. It wouldn't be the first option because it only tells you the greatest increase in the x direction for x, and it wouldn't be B because it only tells you the greatest rate of increase in y, but it should be C because it tells you in both 2, 2, which is x and y, and not just the partial derivative with respect to x or y. Okay, because the rate of ascent is just the gradient. Okay, and it wouldn't be D either because D says that it's traveling west, and west is on the opposite side. So yeah, this is how we got C. Okay, now this is a true-false question. Okay, which of the following are true if f is a differentiable function of two variables and has a local minimum at a comma b, then gradient of a comma b is 0? Yes, this is true because that's the definition of local minimum and maximums. This is a critical point where our where the gradient is 0. If a function x comma y is x squared, then the gradient of f is 2x. This is false because the gradient of f would be 2x comma 0 and not just 2x. You have to keep in mind that you also, because the gradient isn't just the x derivative, it's also the y, and it's always represented in the form of x comma y. Okay, then for part 3, it asks, okay, so this is just reversed, and this would be true because the order of integration doesn't matter in double integrals. You're still going to get the same answer. Doesn't matter if you take the derivative with respect to x first or y first. So this is true. The gradient is always orthogonal to the level curves or surfaces. This is also true, and we just saw this in part 4 right here. So yeah, so we have 1 true, 3 true, and 4 true, and that's going to be option B right here. Okay, now next question. This question, okay, so you are given the base B, the height h, you're given dB over dt, and you're giving dh over dt. Now you have to find the rate of change of the area of the triangle. Okay, so we know that area of a triangle is just half times BH, and if you take the derivative of that with respect to time, that's going to be half of the b dt times h plus half dh over dt times b. Using the product rule, we know that dB over dt is 2 and dH over dt is -1 since it's decreasing. Okay, so we just plug that in here. Half, I'll put the half, I'll factor the half out, so it's going to be 2 times h, that's 5, and then plus dh is -1, -1 times 4, that's going to be half times 10 minus 4, which is 6 over 2, and that's 3, so it should be 3 centimeters squared per second. Okay, now we've come to the free response part, and up until this point you did not really have to show all of this work, but yeah, it always helps if you do, and there's no credit for showing work, but we just do the work in the space that we're given over here. Okay, for part 2 we have to show all of our systematic work. Okay, and okay, problem 8 asks us to find the directional derivative of this function at this point. So the directional derivative, we first find the gradient in this direction, and that's just fx comma fy, right? So we take the partial derivative with respect to x first. That's going to be 2x times y cubed, and since there's no x term here, that's just going to be 0, so minus 0, which is just 0. And then we take the derivative with respect to y. That's going to be 3y squared times x squared minus 4. Okay, now we take the now we plug in the values 2 comma 1, which is going to be 2 times 2 times -1 cubed, comma 3 times -1 squared times 2 squared minus 4. And this is going to be 2 times 2 times -1, so -4. And this will be 3 times 1 times 4. So 3 times 4, that's 12, and 12 minus 4 is 8. Okay, so this is the gradient in this direction. And now we have to find the directional derivative in the direction of this vector. So the directional derivative is just times the unit vector of v. So we start by finding the unit vector of v. That's going to be 3 over 3 squared plus 4, square root of 3 squared plus 4 squared, and that's going to be 5. And yeah, so 4 over 5. And this comes out because the magnitude of v is 5. Okay. Now we just take the dot product of these two values. So negative 4 times 3 over 5, that's going to be negative 12 over 5, and then plus 8 times 4, that's 32 over 5. That's going to be 32 minus 12, 20 over 5, and that's just 4. Okay. So D I like to always box my answers so that they catch the attention first. Okay, now the next part, we have to evaluate this double integral by converting it to polar coordinates. Okay. Since this is also a double integral, let's just draw out the bounds first. Okay, y goes from 0 to one minus x squared, and this is pretty much the equation y squared plus or x squared plus y squared equals to 1, which is just a unit circle. So our y goes from 0 to this unit circle right here. This is going to be 1. And x grows from 0 to 1. So 0 to 1. Okay. Which tells us that this is the region that we're supposed to cover. This is the region R. Okay. Now, for polar coordinates, we need to remember that x squared plus y squared is r squared, and dx dy, which is just dA, turns into r times dr times d theta. I want you guys to know all of these conversions for cylindrical, spherical, and polar coordinates. Okay. So now we just convert everything in terms of what we know. We have this, so 2 times e to the x squared plus y squared, which is just going to be r squared now, so 2e to the r squared, and dy times dx or dx times dy is going to turn into r dr d theta, and then those bounds. So our first derivative is going to be with respect to r, or radius, and we know that our radius ranges from 0 to 1. So 0 to 1. And then the second derivative will be with respect to theta. So the theta ranges from 0 to, this is 0, and this is pi by 2 in the unit circle, right? And it's clockwise. Oh, sorry, counterclockwise, so it's going to be positive. So 0 to pi over 2. These are the bounds. Okay, so we take the first derivative first. Okay, so for this integral, we can just use u sub. Sorry. So du over 2 would be r dr, and then we can replace. The bounds would be 0 to 1, because the square root of 1 is just 1, and then 2 times e to the r square is going to be u now, and r dr is du by 2. So 0 to 1 eu du, and that's just e to the u, and this is just going to be, if you plug in 1 for u, you'll get 1 e to the 1, which is just e. And then if you plug in 0 minus e to the 0, that's just 1. And then for our second integral, we have to take it with respect to theta. So this is pretty simple. It's just going to be theta from 0 to pi over 2, which is just pi over 2 times e minus 1 minus theta times e minus 1, and theta is 0, so that's just 0, which is just pi over 2 e minus 1. So that's our final answer, pi over 2 times e minus 1. Okay. Yeah, so this is what our solutions should look like. Okay, moving on. Now for this problem, we have to find the equation of the tangent plane to the surface at this point. So in order to find the tangent, we need the normal vector and the point on the plane, right? So we can take this point to be on the plane, and to find the normal vector, we'll just take the gradient of f with respect to x, y, and z. It helps if you write out all the formulas that you're using, because that's where I feel everybody loses points. They show the work, but it's incomplete in the sense that you do not show how you got onto this step without showing the previous steps. And I feel like skipping steps makes you lose points, so it's always advisable to list down every single step, especially for free response problems, because that's where you're getting marked on. It's for the work that we're getting points for. Okay, so our gradient of f would be the partial derivative with respect to x. That's just going to be 1, since there's only this x term over here. And then for y, it's going to be 0 plus 2y plus 0 minus 0 plus 0. So just 2y. And then for z, it's going to be 3z squared minus e to the z plus 0. So 3z squared minus e to the z. Right? Now we calculate this gradient at the given point, which is -4, 2, 0. And that will be 1. 2 times y is 4. 3z squared minus e to the z. So 3 times 0 squared is just 0, minus e to the 0 is -1, because e to the 0 is 1. Okay. Equation of tangent plane is your capital F of x times x minus x naught plus capital Fy times y minus y naught plus capital Fz and z minus z naught equals to 0. Now we plug all these values in here. Our x naught, y naught, and z naught would just be these points, -4, 2, 0. And our fx, fy, and fz would be 1, 4, and -1 respectively. So 1 times x minus 4 would be positive 4. So x plus 4 plus 4y minus 2 plus negative 1, because z is negative 1, z minus 0 equals to 0. Now we'll just simplify this a bit. So this just becomes x plus 4. This would become 4y minus 8, and this just becomes negative z equals to 0. So we just shift all the variables or club them together, and this would become negative 4. Okay, so this is our final equation to the tangent plane, and that's your answer. You can also leave it in this form, like this is also the standard equation, but it always helps to simplify your equation as much as possible. So yeah, that is the solution for this problem, and this shows all the work that's necessary for this problem. Now we move on to the next problem, which asks us to find the local maximum and minimum values or the saddle points. If we do not have maximum or minimum values, we have saddle points, or vice versa. So we start by finding the critical points for this equation, and to find the critical points, we first take the partial derivatives with respect to x. There's going to be 2x plus 2y minus 6, and then we find the partial derivative with respect to y. That's going to be 4y plus 2x plus 8. Let's just find the double partial derivatives as well, because we're going to need them for our discriminant. So f double x would be just 2, and f double y would just be 4. And then we also have to find f xy or yx. They're the same. You can either differentiate this with respect to y or this with respect to x. You'll get the same answer, and that's just 2. Okay, now we find the critical points. So at our critical points, fx equals to 0 and fy equals to 0. So we can factor out the 2, and that's just going to be x plus y minus 3 equals to 0. Now I'll just take this in the form of x, so that we can substitute for x later, and x becomes 3 minus y. Now we take the derivative with respect to y. We do not take the derivative, we equate the derivative with 0. So 4y plus 2x plus 8 is 0, which means that if we factor the 2 out, 2y plus x plus 4 is 0. We can just plug in for x at this point. 2y plus 3 minus y plus 4 is 0. So y plus 7 equals 0 and y equals negative 7. We can, okay, so I plugged this in here, and now we can plug this back here. So if y is negative 7, that means that x is 3 minus 7. So 3 plus 7, that's 10. Okay, so our critical point is 10, negative 10. Now we find what this critical point exactly is, if it's the local maxima or minima. So for that we find D, and D is just the discriminant. Or sorry, I keep saying discriminant, it's the determinant, sorry. And that's 2 times 4 minus 2 squared, because f double x is 2 and f double y is 4 and fxy is 2. So that's going to be 4. And since 4 is greater than 0, this point is either a local maxima or a minima and not a saddle point. Now we can observe the value of f double x and see that that's greater than 0, right? So that tells us an f double y is also greater than 0. Okay, which means that this is a local minima. So which gives us our final answer. That's local minimum at 10 comma negative 7. Okay, so that's our final answer for the 11th problem. And yeah, that's pretty much it. Just keep in mind of how much work you have to show for your free response problems and for and how much time you have to dedicate for your multiple choice problems. That is all. And also do not forget to enlist your answers on this table right here after you're done, because this is what you'll be marked on. This is where you get the points for your multiple choice. Okay, so that is all that I have for today, and thank you so much and have a good one. Thank you.